So today we're going to be looking at some mixed final review for Math 31. This, of course, is in preparation for our final exam. I'm going to be telling you just a few different concepts that you can expect on that final exam and walking you through with some of the questions that you can expect there too. Let's get started. So again, like I just said, just a few selected topics today. The ones we're going to look at are equation of tangent lines. We'll look at an optimization problem. We'll look at vertical, horizontal, and oblique asymptotes, and then we'll look at a special integration technique. Each of these kinds of concepts are things that you could potentially expect to see on that final exam. Let's not waste any time. We're actually going to run through this. I would actually highly advise before you watch this video to make sure that you've actually tried these questions first, and then you can use this kind of as a reference just to see whether or not you've done these questions correctly. Here we go. So first of all, find the equation of the tangent line for this function. So here's the trick here. We're given a function. We want to find the tangent line at this point 223. A tangent line, of course, is a line that just grazes the surface of the function at that particular point. Now, the important thing to understand is if this tangent line is grazing the surface at that point, that tells us that this tangent line must have the same slope at that point as the actual function does. So to determine the slope of this thing, we need to first find the derivative of this function because the derivative tells us the slope of the tangent line, right? So anyway, take the derivative of this, f prime x equals, by the power rule, this squared is going to come down. We're going to have 10x minus, this is just, 2x, so it's going to become 2. And then for the plus 7, the derivative of 7 is nothing, or 0 really, so that's where we're at with that. Now we can take this point of 223 and plug it back into this function to figure out what our slope would be at that point. So we can plug in x is 2 in here. We can't plug y is 23 in here because we have f prime. We don't have y. So let's just start with that 2. If we plug 2 in there, we have 10 times 2 minus 2. 10 times 2, of course, is 20. 20 minus 2 is 18. 18 is going to represent the slope of this function at that point. Now, again, a tangent line is going to have the same slope of this, and a tangent line is a linear equation, which is going to take the form y equals mx plus b. M, if you remember, is the slope of that tangent line. So right now, we know that we have the skeleton equation here of y equals 18x plus b. Now your job is, of course, still to find the value of that b. We want an equation of a tangent line, so we need to leave x and y alone, but we got to figure out what the value of that b is. Well, here's the other interesting thing. Not only does a tangent line have the same slope at that given point, because it's tangent at that point, it's also going to pass, at least very closely through this point 223. So long story short, we can throw 223 back into this skeleton equation of a tangent line to figure out what our b value would be. So now we can plug in that 23. So 23 equals 18 times 2 plus b. 23 is therefore going to equal 18 times 2, which is 36 plus b. And then we can subtract 36 over, and I'm pretty sure we get b equals negative 13. So to finish this question off, we have our equation of our tangent line as being y equals 18x minus 13. So to sum that up again, if we're trying to find the equation of a tangent line, we need to first figure out what our slope would be at that point. And we can use our original function's derivative to find that slope by plugging in our x value. Once you have that slope, you can make it your m in y equals mx plus b, and then use that point that you went through to figure out what your b value would be. All right, anyway, next question. So for this next problem, it's an optimization problem. We're designing an open top box that must have a square base using a single piece of cardboard that has a surface area of 108 inches squared. What dimensions will produce a box with maximum volume? So here's the trick behind these ones. We have to figure out what we're actually maximizing. What are we optimizing in these questions? And the question directly tells us that we're maximizing our volume. Now, the reason that's important is the thing that you are maximizing is going to be the thing that you'll be taking the derivative of. Remember, a maximum happens where the derivative is equal to 0. So first of all, if we draw a picture of our open top box, it might look something like this. We got our box here. This is going to be the front panel. It's going to go back this way and then over, something like this. It's an open top box, so this is going to come down. It's not the perfect looking box here, but you get the idea. So we got our box. This box is going to have dimensions of width. Height is going to come up this way. Now it did say it has a square base, so instead of calling this length going back, I'm going to call it another width. The volume of this box, because it's just a rectangular prism, is going to be your width times your height. So again, volume is going to equal width times height, so that would be W squared times height. Now, the trouble here is if we were to take the derivative of this volume function, we have two different variables we're working with within that formula. We have a W and we have an H. That's not exactly ideal. That's where you take in the consideration of any other piece of information that the question gives you to try to come up with an expression where you're only working with one variable. The surface area of 108 inches squared is going to prove useful for that reason. If we think of the box's surface area right now as the square base plus the area of the four sides, the surface area can be thought of as the area of the base, which is W squared, plus the area of the four sides, which would be 4 times WH, because each of those four sides is just an H by W square, or a rectangle rather, so 4WH. Now we know the surface area is 108, so I might as well just say this is equal to 108. It would be really great if we got one of these variables now by itself. I think the clear option here is to get H all by itself because there's only one H in this expression, and yet there's a couple different W's there. So here's what we're going to do. We'll subtract W squared over, so this gives me 4WH equals 108 minus W squared. Then we'll divide by 4. So this gives me 4W. This will give me H equals 108 minus W squared over 4W. Now that I have an expression for H, I can now substitute this back into the other formula over here. This will give me V equals W squared times, instead of H, I'll write this as 108 minus W squared over 4W. Now, one nice thing about this is if we're multiplying this W squared in, it's just going to hit the top. But because there's a W squared here and a W on the bottom, maybe it'd be easier for us just to cancel out one of these W's, and then we only have a single W to double dip through the top there. So this gives me volume equals 108W minus W times W squared is W cubed over 4. Now, we could take the derivative of this, but this is a fraction. And honestly, I don't like taking the derivative of fractions, even though the denominator here is just a number. So I'm actually going to divide each of these separate things on the top by that 4, right? That way I don't have as big of a fraction to worry about. If I do that, what I'm going to get is 108 divided by 4 is 27. So this is 27W minus, as for W cubed divided by 4, not really any way around it. It's just got to be W cubed over 4. So finally, I'm at a point now where I feel comfortable. I can take the derivative of this expression right here. So if I'm going to do that, I'll just do this way over here on the left side. We'll call it V prime equals the derivative of 27W, which is just 27, minus the derivative of W cubed over 4. Well, the cube's going to drop down, so we'd have 3W squared over 4. Now, the derivative of the volume just tells us how the volume is changing. We're looking for a maximum volume. A maximum volume is going to be where you have a slope. If this is the volume, it's going to be where you have a slope of 0. So let's set this derivative equal to 0 because it's going to tell us where our slope is therefore equal to 0. From here, we can add this 3W squared over 4 over to the other side. So we have 27 equals 3W squared over 4. We can multiply by 4 to give us 108 equals 3W squared. Then, just because I'm running out of room here, I'll divide by 3 and square root that. What you're going to get is actually W equals exactly 6. And since this is our width and our units were inches squared, the width is just 6 inches. Now, that's the dimensions of the bottom here. The question still is looking for what the H would be because it does say what dimensions will produce a box with maximum volume. So we can take that width of 6 inches and we can plug it into the height formula right here to figure out the height. So height equals 108 minus 6 squared over 4 times 6. And if you throw that in your calculator, you're going to find that your height is going to be 3 inches. So right there, kind of a roundabout way of doing this, we were able to solve this optimization problem. We were able to find our width and our height just by using what the formulas are for volume and surface area, as well as, of course, taking the derivative with calculus. So these optimization problems, they're quite a bit. but make sure you're familiar with the process. Again, if I'm looking for a maximum volume, that's your hint that we have to be taking the derivative of the volume formula. Never take the derivative in these optimization problems of a question that has more than one variable in it. So if I give you some other piece of information, use a formula for that to get one of the variables by itself. Then you can go from there. So definitely a bit of a process, but that's how it's done. So moving on. Next one, asymptotes. It's been a little while since we've talked about this as well. Find the vertical, horizontal, and or oblique asymptotes for this rational expression right here. I'm going to give you a bit of a heads up. Vertical asymptotes are pretty much independent of what type you have. Vertical asymptotes are the ones that only show up in the bottom. You got to check the top as well, just in case, because if one appears on the top and the bottom, it's not a vertical asymptote. It's a point of discontinuity. But vertical asymptotes only appear on the bottom. Horizontal asymptotes, on the other hand, are kind of funny because horizontal asymptotes will only happen if the degree of the numerator is either equal to or less than the degree of the denominator. That's not the case in this case, right? This one actually, the numerator has a higher degree than the denominator. I can tell you because of the fact that this guy has a higher degree numerator than denominator, there's not going to be a horizontal asymptote at all. Just to really understand why that is, the horizontal asymptote is found when you have a limit as x approaches infinity. And in this case, if we plug in infinity into this, the numerator is going to hit infinity a lot faster than the denominator because of that x squared. So in other words, since the limit as x approaches infinity is infinity, there won't be a horizontal asymptote. The only way a horizontal asymptote would happen is if the limit as x approaches infinity is an actual real number. So that just leaves our vertical and oblique asymptotes. Here's how I would suggest going about this one. Before we begin this problem, for the purpose of finding our vertical asymptotes, I would try factoring that numerator if at all possible. The reason I do that is I'm just checking to make sure that an x plus 2 doesn't also show up on the top. This is looking like an adapted sum product rule kind of question on the top. We're looking for two numbers with a sum of -2, but a product of +3, because 3 times 1, +3. Here's where we hit a bit of a wall. There isn't two numbers with a sum of -2 and a product of +3. So if you really wanted to, you could use the quadratic formula to factor this, but I'm going to be honest with you, if it doesn't factor in the first place, it's not going to be worth the trouble. Instead, to make sure that we don't have a point of discontinuity instead of a vertical asymptote, I'm going to acknowledge my vertical asymptote as being, oh, maybe I should say VA for vertical asymptote. My vertical asymptote would just be where your denominator is equal to 0, which would be x equals -2. Just to make sure this isn't a point of discontinuity, let's plug -2 into the numerator. I'll just do this with some mental math, so I'll just say it out loud. If we do -2 squared, that's 4. 3 times 4 is 12. Minus 2 times -2, well, that's minus -4, so 12 plus 4, which is 16. 16 plus 1 is 17. There is no way that -2 is going to make that equal to 0. So in other words, we don't have to worry about it. Our vertical asymptote here is x equals -2. So that one's all well and good. Vertical asymptotes, just where your denominator equals 0, not too terrible. The process is pretty quick. You just have to look at the denominator and just make sure it's not one for the numerator as well. It's oblique asymptotes that are a bit more work. Oblique asymptotes will only happen if the numerator is 1 degree higher than the denominator. Notice how this numerator is a degree of 2 and the denominator is a degree of 1. That tells me right now there is going to be an oblique asymptote in this question. How we find an oblique asymptote is through polynomial long division. It's not the most fun thing in the world, but let's get it set up. We're dividing by x plus 2, so x plus 2 is going to go on the outside. Then we are dividing the top piece here, which is 3x squared minus 2x plus 1. And how polynomial long division works is you just look at your highest degree term and ask yourself how many times this one on the outside will fit into this one on the inside. Or in other words, what would we have to multiply x by to turn it into 3x squared? Well, the answer to that would be we'd have to multiply it by 3x. So if we multiply this by 3x, we're going to get 3x squared, and then 2 times 3x is plus 6x, and let's subtract that away. -2x minus positive 6x is going to be -8x, and let's drop down that plus 1. So now that we have -8x plus 1, what would we have to multiply x by to turn it into -8x? Well, that of course would be -8. So this gives me negative 8x, and then 2 times negative 8 is negative 16. And once again, we're subtracting. 1 minus negative 16 is going to be positive 17. That is going to be our remainder. Now here's the thing. Oblique asymptotes are going to be basically what your function was in the like as an answer when you did the division, right? So the oblique asymptote here is actually going to be that 3x minus 8. There was an official way of checking this, and the whole thing was just making sure that like the remainder had a limit as x approaches infinity of 0. But the reality is it's going to be. I'm not even going to like bother worrying about that, and I don't really expect you guys to need to worry about that either. So long story short, just for the purpose of finishing up this course, oblique asymptotes are just the end result from a polynomial long division when you're dividing a degree of 1 higher than the bottom. So long story short again, our oblique asymptote is going to be y equals 3x minus 8. And we do need the y equals because, again, an oblique asymptote is an equation of a line, so an mx plus b. So there we go. That's what we got for that one. All right, one more question here that I'm going to go over with you guys. It's a special integration one. It says determine the integral of e to the power of x times x dx. There's 3 special integration techniques that we've learned in this course. There was substitution, which was great for chain rule questions. There was partial fractions, which were really good for quotient rule style questions. And then there was parts, which was really good for product rule type questions. When we look at something like this, we see e to the power of x times x. I'm not seeing any chain rule piece because this inside part of e to the power of x, like the x itself, there's nothing else going on there. It's also definitely not a partial fraction question because partial fraction questions are quotient rule style questions which look like rational expressions, like in other words, big fractions. That leaves integration by parts. Maybe we'll try tackling that. Integration by parts is the one that says, it's on your formula sheet, it says the integral of u dv equals uv minus the integral of v du. The key to an integration by parts is to realize the question that you started with was composed of a u and a dv. Now the point behind tackling these problems is I've always said set your u to the thing that's a little easier. Between x or e to the x to the e to the power of x and just x, between those two things, the thing that looks easier and the thing I'm more likely to set as my u is going to be that x. So I'll say u is going to equal x. It's a good idea to check for du because du is going to go into this side of the equation here. So du is the derivative of x. Well, that of course would just be 1. The other thing that we had to start with was our dv. dv in this case is going to be the other piece, so it'll be e to the power of x. And then v, this is always the hardest part, we have to just find v by taking the integral of e to the power of x. Here's where we're in luck. The integral of e to the power of x is actually really nice. It's literally just e to the power of x. So there wasn't really a lot of work that we had to do on that one. Anyway, let's give this one a shot. So if we now expand it out using this form here, this integral, which is this part of it, equals u times v. So u is x, v is e to the x, and then minus the integral of v, which is e to the power of x, du, which is just 1. Now we still need like a pointer here, like a differential to like actually point to what kind of integration we're doing here. So because of this, I'm just going to put a dx here because we have an x going on. If you left that out, it's not great. You really shouldn't. But again, it's nice just to point what kind of variable we're taking the integral with respect to. Anyway, now that we have this set up, we have to actually complete the second integral on here. So we have to now take the integral of e to the power of x with respect to x. Once again, the good news to that is it's not a crazy one. So this is just going to be x, e to the x, minus the integral of this is just e to the x. Now, we're not quite done. There's one final step we have to do here. Notice this integral we started with was an indefinite integral because there's no numbers on the top and the bottom. That means we always have to remember to finish this off by saying plus c. And that actually finishes that special integration off just there. So that takes us to the end of that. That was quite a lot of review. Again, hopefully you were able to complete those questions on your own first and then watch the video to understand that. Anyway, so we finished finally all those questions. here's the information for your final exam, basically. So your final exam will cover all of that information that you see on there. A lot of that stuff that you see in that list is stuff that we've covered today, especially stuff like creating tangent lines or optimization or vertical, horizontal, oblique asymptotes and special integration. But there's other things on there that we haven't been able to touch on today just for the sake of time. So it is your responsibility to make sure that you're reading through some of your old notes packages. Those are full of examples, of course, that you can use to study. Any of those concepts that you see on the page right now are ones that you can expect on that final exam. Your final exam is entirely written response. It's 6 questions on part A, 5 questions on part B, and that typo at the very bottom there should say out of 36 marks in total. If you have any questions about any of this stuff, please make sure you are going to ask. Best of luck.